Hi, in this video we're going to start working on our DLX architecture simulator by creating a finite state machine. So if you're unfamiliar with what a finite state machine is, it is essentially a machine that can be in one of a finite number of states. And when it is in a state, it is only in that state. So most programs can be thought of as being in finite state machines, and can very easily be designed to be in finite state machines. But the reason that our architecture simulator works so well in a finite state machine is because we're going to be in one of 5 states at every single stage of execution. We'll either be in the instruction fetch stage, instruction decode stage, the execution stage, the memory access stage, or the write back stage. So it works very well to have our architecture simulator running in a state machine. So today we're going to start by working on that. So I've just created a project in Visual Studio, and I'm going to start by creating a new file, and we'll call it main.c, and we'll start by we won't put the we'll leave the void in there, and we will return 0. So to create our state machine, we're going to need to actually have a state machine. So let's add a new item, and we'll add another file, and we'll call it state machine.c. And you don't need to follow my naming conventions. If you don't like, you can use whatever you want. But so add another one, and we'll add a header file this time, and we'll call it state machine.h. Okay, so I don't feel like using Visual Studio's conventions, so we'll remove the pragma. So we'll include the state machine file, and I don't know what kind of pop-ups I'm going to have that are Visual Studio specific, but I'm running the ReSharper toolkit, so some stuff may come up that people aren't familiar with. That's what it might be, so just as a heads up. So let's set up our headers, our header guards for this state machine header. So if in def DLX state machine h. Actually, I'm going to remove these leading underscores. There's no real proper or real there's no real standard on how to name these. You can really name them whatever you want. It's just if you start getting into some kind of crazy stuff, you may end up with duplicates with system headers, which isn't always a good idea. But this should be a safe one. I like to prefix the project that I'm working on with the header guards. So that's why it says DLX at the beginning, but that's just personal preference. So now that we have a header and a source file, we can start with actually setting up our state machine. So our state machine is going to need to know, we're going to need to know the current state we are in, what state we're going to transition into. Actually, we should say, so we need to know the current state. We are going to need to know when to transition and where to transition, and we should know the current state of the registers as well. So to start off with, we need to set up some variables here to store stuff like current state, and when to transition, where to transition, everything like that. So let's start by creating we need to create our state machine. We need our state machine to be something. So I think we're going to let's make a struct, and we'll call it our state machine. And in it we can have, so I'm just going to use comments for now, and then once we start putting things into place, we can remove these comments or reword them. But so we're going to need the current state, and registers. So that should be pretty simple. That should be basic and good enough for right now. So let me just give me an error that's empty. Yeah. So that's just because it's empty right now, but that should be fine. We'll clean that up in a little bit. So let's create another source file. So I guess source file, and we'll call it state handler.c, and we'll create a appropriate header file. State handler. So the state machine is what's going to do the actual processing of states, and what the state handler is going to do is it's going to handle stuff like preparing a state. So once we enter in, making sure everything's prepared to execute whatever needs to be executed in the state, and then also the cleanup. So it's going to handle the entering, the exiting, and the life of the state, whereas the state machine is just going to handle transitioning between states. So we'll do another if and def. If not defined, DLX state handler H. Pretty sure that matches what we had before. Yeah, and then we'll define it. And then endif. Alright, so now that we have that, we're going to need to have our states. So let's call it, let's make a general state struct right now. And it's going to need to know, what will it need to know? Oh, spelled that wrong. Okay. So type def struct state, and here we have type def struct state machine. So in here, we're going to need to know, actually, there's anything right there right now, I'd say. So let's create a variable. So we're going to need to import the state include, I guess we should include, not import, state handler.h, and then we can have current state. We can have, what do we call it? We call it just a state variable. So state, current state, and then let's put just not assign anything for now. So I should actually go in the state machine, not here. So current state, we can do state current. Actually, let's make it a pointer. Current state. Okay, so this stores our current state now. So let's make another source file, and we'll call it source. We'll call it register. I should call it register registers. Let's call it register file handler. And then we'll add in a header file to accompany it. Register file handler.h. Oh, that's an ht, not an h. Let's rename, change it to a .h file. So let's go if and def DLX register file handler H. Define DLX register file handler H. Oh, and then endif. So this is going to need to store all of our registers. So let's create another struct, and we'll call this one registers. Let's create a type def up here. Type def unsigned int uint. We'll call it DLX. Actually, no, there is no uint. Okay, so type def. There's no built-in uint in here, so let's create one. Unsigned int uint. So Um, the deluxe architecture has 64 registers. Um, all of them are 32 bits, with 32 of them being general purpose. So 32 general purpose registers. And then it has 32 floating point registers that, so these are 32 single precision, or, I think I spelled precision right. I don't even know. Precision. Oh, well, whatever. Or they are 16 double precision. I'm going to Google how to spell precision. It's one too many S's. Okay. Oh. Okay. So they are 32 bits, so we can use an unsigned integer. So uint r0, uint r1, uint r3, and uint r2. Now the one special one is r0, which I guess we can't do an assignment. Yeah. Wait, we can with a const. So let's call it const. So R0 is always 0. So that's one of the only ones that's a catch. So I guess we can put all of them in now. It's just a lot of unnecessary, or a lot of boring typing. R7, uint R8, R9. Uint R13, R14, uint R15. There's got to be a faster way. Actually, if we do this once, R16. I guess we can copy these. And then just replace the 2's, the ones with 2's, and then uint R30, uint R31, R32. Oh no, so it's there, 31. We forgot 30. Alright, so now we have 0 and then all the way through to 31. So I think we can, we can't fold these. So now we have the floating points, which are they're also 32 bits, but actually I think these might be better off using. Now we'll leave them as ints right now. So F0, which isn't always 0. F1. Actually, we can just duplicate this. Actually, let's switch this to type def, just to separate things. Struct GP registers. Actually, yeah, GPR registers, and then type def struct FP registers. So these will be our general purpose and our floating point. And we can switch that to that, and we can have in here, we can have FP registers. Oh, these gotta be above, that's why. So move these below. And okay, so now we can paste in here. Oh, I erased it all. Should have pasted before I moved it. Well, that kind of sucks. So I guess we will use just a few registers for now, and then I will update that later. So GP registers, GPRs, and FP registers, FPRs. Oh, okay, FPRs. Okay, so these can be pointers to these, and then these will have the actual values in them. So uint, so f0, f1, f2, and then this one will be const uint r0 equals 0, and then uint r1 equals 1, 2 equals 2. Okay, so these will be just for testing right now. So the register file handler, source file, yeah, we'll probably make use of that, but for now we'll just leave it empty. So the state machine needs the registers, so we will include the register file handler, and then we will have registers, and we'll call them just call them registers, I guess. So we got a current state, and we have our registers. So that's pretty good right now. So in our main, we're going to want to remove this from the comments, but we'll create a state machine. We'll call it SM, and then state. So we should, inside here, we'll create a function, include state machine, and we'll have a function, we'll call it void initialize state machine, or it was called yeah, we'll call it initialize state machine. We won't take any parameters for now, but actually we should return an int, and we'll return 0 for now. We'll just say, actually, oh, not that. Let's go in here, and we need to functions declarations. So we're going to declare our function here. So int initialize state machine, and so that's so we can call it from main, and we'll also put in some. We'll call them constants. Define ready, or we'll go state machine ready and 0, and then state machine loading 1, or initializing 1, define state machine not initialized. And we're just using these to track the state of the, actually just switch these two around. So let's just kind of track the state of the state machine not initialized. We'll set that to 0, and then define initialized as 1, and then define, that should be good for now. So this is just for us to kind of keep track of where the state machine's at. So let's set a variable that is static. So global variables. So let's create a static int, and I guess we could use a short or something, but I'm not really concerned about memory usage right now. But so we'll call it static int state machine. So sm status equals sm not initial. Let's go ahead and define sm not available, or sm not exists. So this is just for a default value. So we call it exists. I pressed the no, okay. So there we go. So we have a sm status sm not exists. Let's actually prefix this with like some kind of some kind of a way to tell it's a global variable. So we know that we're going to be accessing from everywhere. I should put a semicolon in front, or an underscore in front rather. So here we can say sm status equals initialized. Oh, not that. sm initialized. Okay, so right now all our initialization routine does is says it's initialized. So we can go to and have a in here now we can say sm, or actually let's pass in the state machine. So let's pass in the state machine into the initialize state machine, and then pass in sm. So this actually makes a pointer then. Start passing the same one. Then make that the address, and then the pointer. Okay, so we can go, actually let's put the status into the state machine. Let's not put it as a global variable. So we'll say int status, and then in here, so let's say, put another one in, int create state machine. So we will create it, state machine, yes, that doesn't exist anymore. So we're going to create a machine, we're going to initialize a machine, and then actually, instead of passing these in, let's say sm equals create state machine. So now we don't need to pass in these variables. So in here, we will put our declaration for initialize. So we're going to we're going to leave initialize local to this file. Initialize state machine. And that's because we're going to have this function, create state machine, call initialize state machine. So this is going to return a state machine as a pointer. So, oh, it doesn't want me to put that in brackets. So we'll just put that up again so we know it's a pointer for the state machine variable. So let's go back to state machine.h and change this to state machine, and then create state machine. So now that's good. And here we are calling create state machine, and it returns us a state machine that we can then use. So create state machine is going to go to an. So let's put this on to this side here, just so I can see both at the same time. So we've got int status, current state, and registers. So let's go to an state machine pointer sm equals state machine. We'll cast it to a state machine pointer, and then malloc, and we'll say, well, malloc, let's say that does. No, I don't want that. So it will include stdlib to give us access to malloc, and we will malloc size of state machine. So this is going to allocate us the memory for our state machine, which is effectively creating the state machine, and then we will initialize state machine, and we'll pass in sm. So, and then what we'll do after that is we will return sm. Okay, so we're going to create our state machine, initialize it, and then return it back to main, which will then use it to start up our state machine in our simulator. So in the initialize, we're going to want to actually right here, let's set it right here inside the create. SM status equals SM not exists. Actually, no, we don't need that anymore. So let's set it to, so let's set up these variables. Status equals SM not initialized. And then we'll set up the current state to be null, and the registers to be null as well. So this is just our way of having default values so that we can check when we get back to main to make sure it's been initialized. Because we will get an object back regardless, because we've malloc something, but we want to make sure that it's been initialized. And I mean, we will catch the return value here. So int status. So we'll set this to equals 0, and then status equals what's returned. Actually, just change to ret status, so we know what we're. So we can kind of, just for easy naming, but. So let's start by returning 0 for now. So in this, we're going to need to set up the current state, and then from there set up the registers. And the one nice thing about writing a simulator in software is you can easily avoid problems where with real hardware, when you access a register that hasn't been cleared first, it can have a random value in it. And the nice thing about writing something like this is we can have control over that, and we can set it up to initialize all the registers to 0, or set them all to a certain value, or random values if we want to simulate not clearing it, or however we want to do that. And that really depends on what the purpose of this machine is. For something like that's educational based, it makes sense to have the values randomized so that you realize the point and the purpose of clearing your registers first. So how we want to approach that, I don't know yet, but it's why we have the ability. That's why we have this here to set up the registers. And then on successes, we want to have SM status equals SM initialized, and then return SM initialized. And then if SM, I guess we should have this as an error of some kind. So define SM initialize error equals 2, or S2. Yeah, that should be good. We'll say that. So if yes, we'll go if ret status does not equal SM initialize. So actually, one thing I learned from a professor of mine was to always put your constants on the left. So stuff like define is it's not going to be, you can't change it by going SM initialize error equals 1. It gives you an error because it's not a modifiable value. So what he taught us to do is always put that value on the left. So that way, if you ever make a mistake of putting in equals, because if you were to use int p equals 0, and if you were to go if p equals ret status, this is a valid statement because it's assigning ret status to p, and then it checks p to see if p is positive or negative, or 0 or non-zero rather, and if it's 0 it's false and this never executes. But if ret status, if we return SM initialized to status, or to ret status, and then we were to assign it to P, this would be now equal to 2, and it would be true, meaning whatever's in here is executed, even if we didn't want it to be. So by putting your constant value on the left-hand side, you'll always get an error if you try to initialize this. So you'll know if you are initializing or you're not using the right comparator or operator here. So that's why it's a good practice to do that. And I don't do it enough, but I will do it here. So if we have an error, we can handle it in many ways. I guess depending on what kind of an error it is. So let's actually make a new item, a header file, and we'll call it errors.h, and we'll say if and def DLX errors h, define DLX errors h, and if. So this is basically going to be a file for us to put all of our different error defines in. So define sm general init error equals -1. Oh, I guess I don't need that. Equals. And I like to tab over my values so it's all clean looking. So then define sm register init error as -2. sm let's see, state init error -3. So we can remove this one then. I guess we have, yeah, that's general init error. Okay, so save errors.h, and then inside our state machine we can import it, include it, I mean, errors.h. And now inside of, where'd it go? State machine.c. So we can remove this. So if 0, again, it's a constant value, so you can't assign anything to 0. So put it on the left-hand side, is greater than ret status, meaning that our return status is a negative value, which would make it an error value. Then we want to handle whatever. So we can handle this however we want. We will log this in the future. It's always good to have a logger of some kind because you can kind of see what happened. But we'll log this, and then we will destroy. I haven't used unmalloc. I forget how to unmalloc things. Delete? I'm going to look that up really quick. I haven't unmalloc things in a long time. I want to say it's delete. Free. That's what I'm looking for. What we'll do is we will free the state machine, and then we will say sm equals null, which I guess is the same thing. And we'll return state machine. Or actually, rather, instead of doing that, we can say sm status equals, actually let's create a variable in here and we'll call it int error. So we'll set error to be ret status. So this way we can kind of see what happened. So we'll set error to error equals, so we'll have one here, define sm no error equals 0. So that's just a default value for it, so sm no error. And then we can set the error value and then return it. So now if we go back to main, we have a state machine that's created and returned, and then we can check if sm error equals, or if sm no error does not equal sm error, we can destroy state machine and then return. So basically we're going to see if there's an error when we create our state machine. If there's not, we're going to go ahead and do stuff. Otherwise, we're going to destroy the state machine and return and exit the program. So let's create a function. So void destroy state machine, which is going to take in a state machine. And then we'll write the actual definition of it. Destroy state machine, So we're going to need to clean up state, clean up registers, and then free SM. So this just makes sure that everything's all nice and cleaned up and there's nothing floating around in memory. So let's put this back here. And so now if we go through, we kind of have a lot of stuff going on, but it's pretty simple. So actually we should pass it in here, the SM. So, and then if state machine. So let's make a state machine here. We'll call it void run state machine. So here, we're not going to do anything yet because don't need to do anything yet. So state machine C and state machine.h void run state machine. Okay, so I forgot to pass it in again. SM. Okay, so we start off by getting a state machine by calling the create state machine function, which will let's get rid of all these spaces here. So we start off by creating a state machine where actually let's set, I'm really bouncing over the place here, but let's set general init error to be the default value of ret status. General init error. So this is just so that way if for some reason something happens and we're returning, you know, if something here happens, or it's just a way to give us a default value, I guess, for whatever reason. So we have a general init error as the default value, meaning something didn't go right, because it's better to assume error than to assume success. So we allocate the memory for our state machine. We set the status to be not initialized. We set the error to be no error, since there hasn't been any yet. And then we set the current state to be null and the registers to be null. And then we go to and we initialize the state machine, where we set up the current state and we set up the registers, and then we set the status to be initialized, and there's no error, so nothing changes. And then inside of we set return initialized or the status, whichever we prefer. And then if everything's good, we return the state machine. If something goes wrong, we set the error and we log that there's an error, and we set the error to be the return status. And then back in main, we would handle the error. So we basically check if there's no error. If there is an error, we want to destroy the machine and exit the program. And we can do more logging here, log this, and all kinds of stuff. So, and the destroy state machine is going to clean up the registers, clean up the state, and free the state machine. And then if we don't get any errors, we're going to run the state machine, which will actually start executing things. And we've got our errors.h for our errors. We have our register file handler for, I don't know why I have these equals in here. Good thing I saw that. And why is this giving an error? uint or const uint r0 equals 0. Weird. I don't know why it's giving an error. Because last time that's what we had to do. Let's go uint r0 equals 0. Well, now it's not letting me. We'll have to fix that for next time. Why it's not letting me assign. So, anyways, we have our register file handlers, which will store our registers, and then our state handler, which will handle all of our states. So that's where we'll stop this time, and next time we'll start working on we'll start implementing states and handling the transition of states and all that good stuff. The code will be on my GitHub, which I will include a link to in the description of this video, and then if you want to look at it or you want to use it, it'll all be available up there. I'll probably take some time in between recordings to apply more comments, and kind of clean things up a little bit, just stuff that would be boring to watch, and then I'll make sure to let you guys know in the next video what I've all changed in between the videos, and hopefully the next video will be up in the next few days, so you can check that out if you're interested. And until then, happy programming.